Hello and welcome everybody to section 9.3, the general solution to the vector differential equation x prime equals ax. Now, when A is an n by n matrix, we need n linearly independent vector solutions to form the general solution. So first theorem, the set of solutions to x prime equals ax, where A is an n by n matrix, function of t, that is continuous on some interval t is a subspace of dimension n. So the solutions to this vector differential equation, where A is an n by n matrix, is a subspace. Now, consequently, okay, if x1, x2, and xn form a linearly independent set to x prime equals ax, then the general solution to the differential equation takes this form, okay? So what you want to do is you want to think of these as a list of vectors, okay? But instead of vectors where the inputs are all scalars, think of them as functions, okay? So in x1, if n was 3, so A was a 3 by 3 matrix, okay? X1 might look like cosine t, sine t, and t squared as first row, second row, third row. Something like that, okay? So if this set of vectors is a linearly independent set of vectors that are solutions to x prime equals ax, then the general solution to x prime equals ax is of the form constant times vector 1 plus constant times vector 2 plus and so on to constant times vector n. Okay, so I want you to consider the matrix equation x1 prime x2 prime equals the matrix 4, 2, negative 1, 1, and multiplied by x1, x2. That's the same differential equation that we started with, okay? X1 prime equals 4 times some function plus 2 times another function. The derivative of the second function is negative the first function plus the second function, okay? So this is section 9.1, way back in the notes. Through in section 9.2, what we're able to learn, or I guess in 9.1 and 9.2, is what we're able to do is to take this system of differential equations and convert it to a vector differential equation. Okay, so that's a differential equation of this form, where the left-hand side became the derivative vector, okay, times a coefficient matrix. Those are simply the coefficients on x1 and x2 in this case, times x1, x2. And this is our unknown vector. It's the vector that contains the solutions to our system of differential equations. Okay, so in the next video, okay, we're going to show that the solution to this differential equation right here has x1, okay, this quantity right here, that will be negative 2e to the 3, 2e to the 3, 2, and x2 will be e to the negative 2t, e to the positive 2t, okay? And so the way you want to think of this, okay, because this x1 right here, x1 vector, is different from this x1 right here, okay? So the way you want to think of it, okay, is let's come up with an analogy here. Let's say that x1 and x2 are the solutions to a system of differential equations. And each solution has a first component and a second component. So the first solution, the first unknown function, has kind of like a first name plus a last name. And the subscripts right here are notating the first component of the first solution and the second component of the first solution. And the second solution is going to have a first component. Think of it like a first name and a second component. Think of it like a last name. Okay, well, this part that's right here that goes into the first component is oops, sorry, I wrote that wrong, is going to be contained in the vector x1. So first 1, first 2, plus second 1, second 2. Okay, and this is the vector x1 of t. This is the vector x2 of t, which is different. Okay, these things right here are different than x1 of t and x2 of t. Okay, and this is the notation that you're seeing in the book. Okay, so it's not my notation. It's somewhat confusing, and I apologize for that, but I didn't have a vote in this. Okay, where, in other words, the solution to the differential equation. So you kind of look back to section 9.1. Okay, x1 of t is 2c1 e to the 3t minus c2 e to the 2t, and x2 of t is c1 e to the 3t and c2 e to the 2t. These were the two functions that solved this system of differential equations. Now, each one of them has a separate component. Okay, it has a first component and a second component. Okay, the first component looks like c1, okay, times negative 2 e to the 3t and e to the 3t plus c2 negative e to the 2t and e to the positive 2t. Okay, so I can rewrite x1 and x2, okay, to look like a scalar times this vector plus a scalar times this vector. This part right here is what the book is referencing as x1 of t. This right here is what the book is referencing as x2 of t. So it's as though each of these functions, x1 of t that has a first name and a last name, and x2 of t that has a first name and a last name, well, the first names are contained in the vector x1. The last names are contained in the vector x2. And when you add up this linear combination of scalar times vector 1 plus scalar times vector 2, you're able to get to the first and last name for each of the functions x1 and x2. Okay, so make sure before you move on that you understand the difference between little x1 of t and the vector x1 of t, and the little x2 of t and the vector x2 of t, because that's where you can run into some confusion coming forward. Okay, all right, now for the time being, okay, you're going to assume, and again, we will show this, that the vector x1 is negative 2 e to the 3t and e to the 3t, and x2 is negative e to the 2t, e to the 2t. Okay, those are vector solutions to our differential equation. So by this theorem right here, okay, they form a basis. Okay, remember back to right here, for an n by n matrix, we need n, so in this case, 2 linearly independent vector solutions to form a general solution. The set of solutions to x prime equals ax, where A is a 2 by 2 matrix of T on continuous a function's continuous on some interval t is a subspace of dimension 2. Okay, so anytime you have two linearly independent solutions to this, then the general solution is scalar times vector 1 plus scalar times vector 2. Well, there's vector 1, there's vector 2. So the theorem above says the general solution to x prime equals ax is scalar times vector 1, that's this one that I'm going to demonstrate in another video, is a solution, plus scalar times vector 2, that's this one. Okay, so when you look at the linear combination, that's c1 e to the negative e3t, c1 negative 2 e to the 3t, that's right there, and minus c2 e to the 2t, that's right there, and likewise c1 e to the 3t plus c2 e to the 2t. Okay, that's what the general solution is. X is equal to this. The top row is one function, looking at the top row of this vector, gives you the x1 function that solves the system of differential equations. The second row gives you the x2 function that solves the system of differential equations. Okay, so now the question that we are going to answer is, how do you come up with x1 being negative 2 e to the 3t, e to the 3t, and x2 being negative e to the 2t and e to the 2t? Because really what we've done up to this point is I've stated that these two functions solve this system of differential equations and asked you to prove it, and we did in video 1. Okay, and then I've just stated that knowing that the general solution to the system of differential equations is going to take this form. I told you what vector 1 is. I told you what vector 2 is to that same differential equation, vector differential equation. And by the theorem says that this is going to be the solution. So now we know how to output what the solution is. The only thing we don't know is how to come up with what x1 and x2 are, the vector function, the vector x1 and x2. Okay, and so that's what we learn in section 9.3. So again, 9.2 and 9.1, 9.2, and 9.3 are small bites at really what our goal is, and our goal begins in section 9.4. Given a system of linear differential equations, so a system of differential equations, okay, solve that system, find the functions that solve that system, okay, and that's going to come in the very next video. So there's 9.1, 9.2, and 9.3, okay, all to gear us towards solving the questions that are going to be posed to us in sections 9.4, and then a more abstract version of it, the same problem in 9.5.